Writing automated tests. In his 1972 essay, The Humble Programmer, that's a name, Edsger W. Dijkstra said that program testing can be a very effective way to show the presence of bugs, but it is hopelessly inadequate for showing their absence. Hashtag Rust. That doesn't mean we shouldn't try to test as much as we can. Correctness in our programs is the extent to which our code does what we intend it to do. Rust is designed with a high degree of concern about the correctness of programs, but correctness is complex and not easy to prove. Rust's type system shoulders a huge part of this burden, but the type system cannot catch every kind of incorrectness. That being the case, Rust includes support for writing automated software tests within the language. As an example, say we write a function called add2 that adds 2 to whatever number is passed to it. This function signature accepts an integer as a parameter and returns an integer as a result. When we implement and compile that function, Rust does all the type checking and borrow checking that you've learned so far to ensure that, for instance, we aren't passing a string value or an invalid reference to this function. But Rust can't check that this function will do precisely what we intend, which is return the parameter plus 2, rather than, say, the parameter plus 10 or the parameter minus 50. That's where tests come in. We can write tests that assert, for example, that when we pass 3 to the add2 function, the returned value is 5. We can run these tests whenever we make changes to our code to make sure any existing correct behavior has not changed. Testing is a complex skill. Although we can't cover every detail about how to write good tests in one chapter, we'll discuss the mechanics of Rust's testing facilities. We'll talk about the annotations and macros available to you when writing your tests, the default behavior, and options provided for running your tests, and how to organize tests into unit tests and integration tests. How to write tests. Tests. That's going to get old. Tests. 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 Test. Tests. I'm going to say tests. T-E-S-S. Tests. Tests are Rust functions that verify that the non-test code is functioning in the expected manner. The bodies of test functions typically perform these 3 actions. Number 1, set up any needed data or state. Number 2, run the code you want to test. And number 3, assert the results are what you expect. Let's look at the features Rust provides specifically for writing tests that take these actions, which include the test attribute, a few macros, and the should panic attribute. The anatomy of a test function. At its simplest, a test in Rust is a function that's annotated with the test attribute. Attributes are metadata about pieces of Rust code. One example is the derive attribute. I pushed all the wrong buttons. Hold on. One example is the derive attribute we used with structs in chapter 5. To change a function into a test function, add hash test attribute on the line before effin. When you run your tests with the cargo test command, Rust builds a test runner binary that runs the functions annotated with the test attribute and reports on whether each test function passes or fails. When we make a new library project with Cargo, a test module with a test function in it is automatically generated for us. This module helps you start writing your tests so you don't have to look up the exact structure and syntax of test functions every time you start a new project. You can add as many additional test functions and as many test modules as you want. Let's explore some aspects of how tests work by experimenting with the template test generated for us without actually testing any code. Then we'll write some real-world tests that call some code that we've written and assert that its behavior is correct. Let's create a new library project called adder. The contents of the lib file in your adder library should look like listing 11.1. For now, let's ignore the top two lines and focus on the function to see how it works. Note the test annotation before the fn line. This attribute indicates this is a test function, so the test runner knows to treat this function as a test. We could also have non-test functions in the tests module to help set up common scenarios or perform common operations. So we really do need to indicate which functions are tests by using the test attribute. The function body uses the assert equals macro to assert that 2 plus 2 equals 4. This assertion serves as an example of the format for a typical test. Let's run it to see that this test passes. Run. Oh, that's not what I meant to do. C test. The cargo test command runs all tests in our project as shown in a listing 11.2. Cargo compiled and ran the test. After the compiling, finished, and running lines is the line running one test. The next line shows the name of the generated test function called it works and the result of running that test, OK. The overall summary of running the test appears next. The text test result OK means that all the tests passed, and the portion that reads 1 passed, 0 failed totals the number of tests that passed or failed. Because we don't have any tests we've marked as ignored, the summary shows 0 ignored. We also haven't filtered the test being run, so the end of the summary shows 0 filtered out. We'll talk about ignoring and filtering out tests in the next section, controlling how tests are run. The 0 measured statistic is for benchmark tests that measure performance. Benchmark tests are, as of this writing, only available in Nightly Rust. See the documentation about benchmark tests to learn more. The next part of our test output, which starts with doctests adder, is for the results of any documentation tests. We don't have any documentation tests yet, but Rust can compile any code examples that appear in our API documentation. This feature helps us keep our docs and our code in sync. We'll discuss how to write documentation tests in the documentation comments as tests section of chapter 14. For now, we'll ignore the doctest output. Let's change the name of our test to see how that changes the test output. Change the it works function to a different name, such as exploration. like so. Then run cargo test again. The output now shows exploration instead of it works. Ah, crud. I may have not recorded when I meant to, recorded when I didn't mean to. So, here's some text. Alright, test that fails. Okay, adding a second test that will fail because we call the panic macro. Run the tests again using cargo test. The output should look like listing 11.4, which shows that our exploration test passed and another failed. Okay, failed. Instead of okay, the line tests I guess no one really cares about seeing all this. Right. Sorry. Instead of okay, the line test tests another shows failed. Yeah. Two new sections appear between the individual results and the summary. The first section displays the detailed reason for each test failure. In this case, another failed because it panicked at make this test fail, which happened on line 10 in the lib file. The next section lists just the names of all the failing tests, which is useful. The next section lists just the names of all the failing tests, which is useful when there are lots of tests and lots of detailed failing test output. We can use the name of a failing test to run just that test to more easily debug it. We'll talk more about ways to run tests in controlling how tests are run section. The summary line displays at the end, overall, The summary line displays at the end, overall, our test result is failed. We had one test pass and one test fail. Now that you've seen what the test results look like in different scenarios, let's look at some macros other than panic that are useful in tests. The assert macro, provided by the standard library, is useful when you want to ensure that some condition in a test evaluates to true. We give the assert macro an argument that evaluates to a Boolean. If the value is true, assert does nothing and the test passes. If the value is false, the assert macro calls the panic macro, which causes the test to fail. Using the assert macro helps us check that our code is functioning in the way we intend. In Chapter 5, we used a rectangle struct and a can-hold method, which are repeated here in listing 11.5. Let's put this code in the lib file and write some tests for it using the assert macro. The can-hold method returns a Boolean, which means it's a perfect use case for the assert macro. In listing 11.6, we write a test that exercises the can-hold method by creating a rectangle instance that has a width of 8 and a height of 7, and asserting that it can hold another rectangle instance that has a width of 5 and a height of 1. A test for can hold that checks whether a larger rectangle can indeed hold a smaller rectangle. Note that we've added a new line inside the tests module. Use superstar We added a new line inside the test module. Use super everything. The tests module is a regular module that follows the usual visibility rules we covered in Chapter 7 in the Modules as the Privacy Boundary section. Because the test module is an inner module, we need to bring the code under test in the outer module into the scope of the inner module. We use a glob here, so anything we define in the outer module is available to this tests module. We've named our test larger can hold smaller, and we've created the two rectangle instances that we need. Then we called the assert macro and passed it the result of calling larger can hold reference to smaller. This expression is supposed to return true, so our test should pass. Let's find out. It does pass, because the correct result of the can hold function in this case is false. We need to negate that result before we pass it to the assert macro. As a result, our test will pass if can hold returns false. Two tests that pass. Now let's see what happens to our test results when we introduce a bug in our code. Let's change the implementation of the can hold method by replacing the greater than sign with a less than sign when it compares the widths. Running the test now produces the following. Our tests caught the bug because larger dot width is 8 and smaller dot width is 5. The comparison of the widths in can hold now returns false. Eight is not less than 5. Testing equality with the assert equals and assert not equals macros. A common way to test functionality is to compare the result of the code under test to the value you expect the code to return to make sure they are equal. You could do this using the assert macro and passing it an expression using the equals operator. But this is such a common test that the standard library provides a pair of macros, assert ek and assert ne, to perform this test more conveniently. These macros compare two arguments for equality or inequality, respectively. They'll also print the two values if the assertion fails, which makes it easier to see why the test failed. Conversely, the assert macro only indicates that it got a false value for the equals expression, not the values that led to the false value. In listing 11.7, we write a function named add2 that adds 2 to its parameter and then returns the result. Then we test this function using the assert equals macro. Let's check that it passes. The first argument we gave to the assert equals macro 4 is equal to the result of calling add2. The line for this test is test tests it adds to ... OK, and the OK text indicates that our test passed. Let's introduce a bug to see what it looks like when a test that uses assert equals fails. Change the implementation of the add2 function to instead add3. Go back up. What just happened? No, don't do that. Yeah, there we go. So now we want to change that to a 3. And test. Our test caught the bug. The it adds to test failed, displaying the error message left equals right. Assertion failed, left equals right, and showing that left was 4 and right was 5. This message is useful and helps us to start debugging. It means the left argument to assert equal was 4, but the right argument, where we had add2 take 2, was 5. Note that in some languages and test frameworks, the parameters to the functions that assert two values are equal are called expected and actual, and the order in which we specify the arguments matters. But in Rust, they're called left and right, and the order in which we specify the value we expect and the value that the code under test produces does not matter. We could write the assertion in this test as assert equals add2 taking 2 and 4, which would result in a failure message that displays assertion failed, left equals right, and that left was 5 and right was 4. The assert macro will pass if the two values we give it are not equal and fail if they're equal. This macro is most useful for cases when we're not sure what the value will be, but we know what the value definitely won't be, if our code is functioning as we intend. For example, if we're testing a function that is guaranteed to change its input in some way, but the way in which the input is changed depends on the day of the week that we run our tests, the best thing to assert might be that the output of the function is not equal to the input. Under the surface, the assert equals and assert not equals macros use the operators equalses and bang equal, respectively. When the assertions fail, these macros print their arguments using debug formatting, which means the values being compared must implement the partial, eq, and debug traits. All the primitive types and most of the standard library types implement these traits. For structs and enums that you define, you'll need to implement partial eq to assert that values of those types are equal or not equal. You'll need to implement debug to print the values when the assertion fails. Because both traits are derivable traits, as mentioned in Chapter 5, this is usually as straightforward as adding the #derive partial-ic and debug notation to your struct or enum definition. See Appendix C, Derivable Traits, for more details about these and other derivable traits. Adding custom failure messages. You can also add a custom message to be printed with the failure message as optional arguments to the assert assert equals, and assert macros. Any arguments specified after the one required argument to assert, or the two required arguments to assert equals and assert not equals, are passed along to the format macro, discussed in Chapter 8 in the concatenation with the concatenator operator, or the format macro section. So you can pass a format string that contains placeholders and values to go in those placeholders. Custom messages are useful to document what an assertion means. When a test fails, you'll have a better idea of what the problem is with the code. For example, let's say we have a function that greets people by name, and we want to test that the name we pass into the function appears in the output. The requirements for this program haven't been agreed upon yet, and we're pretty sure the hello text at the beginning of the greeting will change. We decided we don't want to have to update the test when the requirements change, so instead of checking for exact equality to the value returned from the greeting function, we'll just assert that the output contains the text of the input parameter. Assert result, okay. Greeting, input to greeting. Oh yeah, so we're running the greeting function here, which takes this and etc. Okay, so that comes in, and then now we've got the result. Result contains girl. Got it. Introduce a bug into the code by changing greeting to not include name to see what this test failure looks like. Okay. Yeah. Okay. The result indicates that the assertion failed and which line the assertion is on. Greeting contains name failed. Yeah, there it is. A more useful failure message in this case would print the value we got from the greeting function. Let's change the test function, giving it a custom failure message made from a format string with a placeholder filled in with the actual value we got from the greeting function. Now when we run the test, we'll get a more informative error message. Oh, where is it? There we are. We can see the value we actually got in the test output, which would help us debug what happened instead of what we were expecting to happen. Checking for panics with should panic. In addition to checking that our code returns the correct values we expect, it's also important to check that our code handles errors as we expect. For example, consider the guess type that we created in Chapter 9, listing 910. Other code that uses guess depends on the guarantee that guess instances will contain only values between 1 and 100. We can write a test that ensures that attempting to create a guess instance with a value outside that range panics. We do this by adding another feature, another attribute, should panic, to our test function. This attribute makes a test pass if the code inside the function panics. The test will fail if the code inside the function doesn't panic. Listing 11.8 shows a test that checks that the error conditions of guess new happen when we expect them to. Where is should panic? Yes. Should panic. Function greater than 100. So a new guess of 200. We place the should panic attribute after the test attribute and before the test function it applies to. Let's look at the result when this test passes. Looks good. Now let's introduce a bug in our code by removing the condition that the new function will panic if the value is greater than 100. When we run the test in listing 11.8, it will fail. We don't get a very helpful message in this case, but when we look at the test function, we see that it is annotated with should panic. The failure we got means that the code in the test function did not cause a panic. Tests that use should panic can be imprecise because they only indicate that the code has caused some panic. A should panic test would pass even if the test panics for a different reason from the one we were expecting to happen. To make should panic tests more precise, we can add an optional expected parameter to the should panic attribute. The test harness will make sure that the failure message contains the provided text. For example, consider the modified code for guess, where the new function panics with different messages depending on whether the value is too small or too large. Should panic expected equals guess value must be less than or equal to 100. Okay. This test will pass because the value we put in the should panic attribute's expected parameter is a substring of the message that the guess new function panics with. Ooh. We could have specified the entire panic message that we expect, which in this case would be guess value must be less than or equal to 100, got 200. What you choose to specify in the expected parameter for should panic depends on how much of the panic message is unique or dynamic and how precise you want your test to be. In this case, a substring of the panic message is enough to ensure that the code in the test function executes the else if value greater than 100 case. To see what happens when a should panic test with an expected message fails, let's again introduce a bug into our code by swapping the bodies of the if value less than 1 and the else if value greater than 100 blocks. This time, when we run the should panic test, it will fail. The failure message indicates that this test did indeed panic as we expected, but the panic message did not include the expected string guess value must be less than or equal to 100. The panic message that we did get in this case was guess value must be greater than or equal to 1, got 200. Now we can start figuring out where our bug is. Using resultte in tests. So far, we have written tests that panic when they fail. We can also write tests that use resultte. Here's the test from listing 11.1 rewritten to use resultte and return an error instead of panicking. Okay, so it returns a result, and we have T and E here. T is the empty tuple, and E is a string. So if 2 plus 2 equals 4, then we will return OK with the empty tuple inside of OK's little tuple bubble. Else, string from 2 plus 2 does not equal 4. The itWorks function now has a return type. Result, I really, empty tuple unit maybe? Yeah, I think that might be called the unit. Result unit string. In the body of the function, rather than calling the assert equals macro, we return OK when the test passes and an with a string inside when the test fails. Writing tests so they return a resultte enables you to use the question mark operator in the body of tests, which can be a convenient way to write tests that should fail if any operation within them returns an error variant. You can't use the should panic annotation on tests that use resultte. Instead, you should return an error value directly when the test should fail. Now that you know several ways to write tests, let's look at what's happening when we run our tests and explore the different options we can use with cargo test.